Hello, everyone. This is the CQS regular seminar. It is a great pleasure to have a seminar by Dr. Liu Sun from KIAS. Today, he will talk about U-duality in exceptional field theory. Please.
Okay. So firstly, thank you very much for the invitation. And this talk, I will mainly talk about the recent paper for U-duality and Courant Algebroid in exceptional field theory. And this also related to former work with Ralph Blumhagen on the heterotic double field theory structure presented the Lie Algebroid. So let's firstly review what happened before. And from the basics, so the T-duality is manifested as a global symmetry in double field theory, and which incorporates both the type 2 supergravity and also the so-called the T-dual beta supergravity, and this T-duality represents this decommuting isometries and manifests as ODD global symmetry in the double field theory. So if we consider further and to unify the S-duality in the term of U-duality, then we would need to go on with the exceptional field theory, representing the U-duality from M theory. And many experts worked on this. And this exceptional symmetry group in the exceptional field theory, that would be represented by this ED. So if we consider this coset from this exceptional group and also the maximal subgroup of it, so the coset will give the parameterized scalar field what we get from this reduction in the external dimension. So what happens in the exceptional field theory? So there's the d-dimensional reduction of this supergravity. Let's see the 11-dimensional supergravity. Then a hidden exceptional group would represent U-duality in the manner of a global symmetry. So which means that in the exceptional field theory, there's a global symmetry, which is an exceptional group. For this D smaller than 7, it can be represented in the table. So this is the modular from this coset, and this is the generalized bundle. So people call it the extended generalized bundle, because in double field theory there's only tangent bundle, and with the cotangent bundle is enough. But in exceptional field theory, because there's the M-brane dependence from the M theory, and we would not just need the tangent bundle, but also this wedge products of the cotangent bundle. So when we do the reduction with the dimension 2, 3 till 7, and this exceptional group would be like this for the global symmetry, and the maximal subgroup. So the maximal subgroup with this exceptional group is here. So we see that so what we did in the paper is for SL5 and SO5, so the extended tangent bundle is like this and this. So here this is the wedge products of the tangent bundle. The cotangent bundle. This is the M2-brane dependence lived here, and here's the M5-brane dependence here. So, sorry, I cannot see this. So let's review the generalized geometry in exceptional field theory. The generalized geometry firstly introduced by Hitching with just the tangent bundle and the direct sum cotangent bundle without this lambda 2 here. And this is enough for double field theory, because so you have the same dimension of supergravity and the dual supergravity. so they lived in the tangent bundle and the cotangent bundle so separately. So when you direct sum them, and it's the generalized bundle, the so-called generalized bundle, it's what corresponding to the double field theory. And as we already mentioned for the M theory, this exceptional field theory, we need a larger extended tangent bundle, and then we have something like this. So this kind of generalized the original version of this generalized bundle from Hitching. So in this talk, what we will consider is this bundle. So differently, we are not, so there are so-called section condition, and what people sometimes use is there, for example, for SL5, we have this TM and with the lambda to TM star. And some paper, so if you do most of the strong and simple section condition, then you can kill this part and you go to the study of this tangent bundle as where the normal supergravity lives. But what we are doing here is not considering this kind of a transformation. What we consider is the whole dual generalized tangent bundle. So you see here is this the whole bundle E, and this is the E star. So the TM mapped to TM star, and this lambda 2 TM star would be mapped to the lambda 2 TM, and this would happen. So for the global corresponding to the global symmetry transformation. So the advantage is that in this proper global transformation, not only the string but also the M-brane gets naturally incorporated in this transformation. So we are not doing that to map the relation from M-brane M theory to string, but we map from M3 to another M star theory. Let's see. Okay, so first let's review what happened for people not familiar with the exceptional field theory. And this naturally comes from so M theory, and there's the three form fields. This one, and this kinetic term is represented in this one. So this is a classical action in M theory, and this field string is a partial derivative with the three form, and so the kinetic term is gauge invariant under this gauge transformation. And this is important. What we will come back to this when we try to prove there is a Courant Algebroid can be properly used. So from the duality point of view, this three form can be split to two parts. So this is a classical thing. So the field string is represented by this, and this part is this is the partial derivative of the B field. So this M2-brane here is so it's what's given in this paper. This M2-brane is constructed in the space-time with the metric and also the three form. So the bosonic part of this M2-brane and the action is given by this. So this is the alternative tensor, and if we consider the electromagnetic duality, this can be represented in this way. So the thing in the middle contains this metric and also the three form field, and this is what one can call it a generalized metric. So the generalized metric actually appears naturally when you consider this duality. It's not something one made out. So when we denote this as the generalized metric, what people use in the exceptional field theory, then the action can be simplified, and this this electromagnetic duality can also be expressed in a simple way. So this is the action, and this incorporates the generalized metric. So these are the classical backgrounds we need, and what we are going to study from the title is so the U-duality and the Courant Algebroid. And what is the algebroid? And the algebroid you can it can be illustrated in this picture. So for example, you have so there are 3 elements to define algebroid. There's a vector bundle over the manifold, and also there's need a proper bracket, and there's a homomorphism map. So this map can be, you can choose to map from the tangent bundle to cotangent bundle, or tangent bundle to tangent bundle, or cotangent bundle to cotangent bundle, etc. And the thing is called the anchor. So this homomorphism map is represented by the anchor. And what can be used, for example, in double field theory, when you consider this tangent bundle to a cotangent bundle map, then it represents the T-duality. So this homomorphism map gives you directly the T-duality. And what we checked for heterotic double field theory is this map. So we first do a global symmetry transformation, and then we define this proper anchor. And this anchor gives you the pure T-duality transformation and the field redefinition in a mathematical but a simpler way. So in that paper, we also give all the explicit expression of all the fluxes to the non-geometric flux. And what happened for U-duality? Here, this is for heterotic. So you see there's a actual vector bundle. So you see there's the actual bundle with the gauge field lives here. So in more details, so this is what happened in double field theory, and this is the transformation metric, and this each elements in the transformation metric corresponds to different maps, and this anchor also gives you for different kinds of transformation. So this is what the algebroid. And for Courant Algebroid, again, there are something we need to check. Firstly, the Courant bracket, and the bracket is like this. So there's a Lie derivative, and there's a it's defined like this. So the closure of the algebra, closure of the Courant algebra condition is like this. So there, you see there are 2 indexes here, and this is for the M2-brane dependence included. So again, so to clarify what we consider here is the Courant algebra for the map is to define the map from this whole the whole extended generalized bundle to the dual bundle in this way. So it's called Courant Algebroid. I checked the original paper. It's made by Courant. It's just to incorporate this higher dimensional cotangent bundle. So in the original paper, it was like this. And what we need is there are more terms here. So another thing we need to check to define a Courant algebroid is the Jacobi term. And the Jacobi term is defined like this. To have the, actually, if you computed this, the Jacobi identity is not guaranteed automatically, but with a result like this. So what is important is, remember that when the gauge transformation we had for M theory is with the 3-form flux. Sorry, with the 3-form field, and the flux was a 4-form. So this is the only field in exceptional field theory. So transform under this gauge transformation. And what happened is this Jacobi, for example, here it takes exact form. So if you, when we consider the gauge transformation and the Jacobi, so get vanished. So which means we have a Jacobi identity, and we also have the closure of the Courant algebra under this condition. So this guaranteed we have a proper Courant algebra for exceptional field theory. It's not automatically satisfied, but for exceptional field theory with the only gauge field three form here, this indeed exists. So it makes sense that we study the Courant algebra mapping in exceptional field theory. And let's start with the simple one. So when we have the ED choose D equal to 4, so this gives the SL5 exceptional field theory. And this U-duality is represented by this global symmetry. So it's simply TM with lambda 2 TM star. And this not only, so the formal sum of the vector, so it's a vector plus a 2 form. So it's an extended vector, it's like this. And this defines a 10-dimensional extended space with the coordinates this. So what has been worked out is the generalized geometry can be kind of decomposed into a simpler one, what they call little generalized geometry, with the expert Professor Park also. So it can be denoted like this. So we study what happened for the generalized geometry. We take the generalized geometry as they worked out, and then we map the global symmetry with the transformation like this. So we denote a very general, the most of the general transformation metric in this way, and the map with the only constraint like this. So after a messy checking, and then we find that there should be anchor denoted in this way, and this so it's I didn't expand here, but if you put this thing in, and then you get this, and what we want to have is kind of a there's the anchor and there's the original matrix, and the anchor maps this matrix to the new kind of a U-dual, or you can call it non-geometric matrix in the U-dual framework. So the anchor, of course, the anchor should be the same anchor for this vector field, which is the dual of the dual three form. And this
why do you call it non-geometric here?
It's just to analog to the double field, but it's just a U-dual framework. Yeah. Yeah, you're right. I think not many people call it non-geometric. So
it does not have to be non-geometric. Can be well defined.
Yeah, but it's in the so I think in double field theory it's non-geometric kind of because you are it's kind of corresponding to the T fold, for example. So you don't have a
here you don't talk about patching of two. Yeah, patching. Going to patch it by dual. This is default, but here it is just one rotation.
Yeah, but the bundle is the dual bundle. So for example, the TM map to the TM star, and this. So if you only consider.
Don't rotate over isometry.
I rotate from this.
You don't worry about the isometry. Here it's a generic rotation.
So,
Am I right?
so let's see. So this map, so here, so this whole thing I map to this one. So if you see, it's a bit like this TM go to the TM star for double field theory.
So you rotate even the solution to the section that you fixed.
Yeah, I don't take the strong section condition. I rotate the whole thing. Yeah. I think the exception group is also for the whole thing, right?
Sure, yeah, but to produce 부셔를, for example, you rotate only over section condition, only over the isometric direction. Then you don't have to worry about the appearance of tilde coordinate. You can still stay at the same until the ordinary coordinate, but still generate new solution. But here you are talking about full coordinate.
Yeah, the full one. So I want to, in the transformation, I want to have the ambient dependence all along in the procedure. So I don't want to drop it at any step. So I always kept them. So that's why this whole thing.
Are you going to not imposing any section condition?
Apart from the closure for the algebra, I don't take a section condition. I mean,
This condition you will.
yeah, this we have to take. Yeah, they have to impose.
Then this will reduce.
But this doesn't kill the ambient dependence unless we take this thing to 0. It's like the whole. If we take this part to 0, then it's killed. But if we take this, the ambient dependence can be kept.
Sure.
Yeah. So yeah, here. So we take the map from this to this, and the all in every step we keep the ambient dependence. So the reason that we are studying the Courant Algebroid is because then this Courant Algebroid is defined to keep this the whole thing. It's defined on this. So the Lie algebroid only for this. Okay, so we do the map and what the result after cleaning up a bit, and we get to the result like this. So in double field theory, there's only such a structure appear. There's no extra term, and this extra term appears indeed because of the ambient dependence was kept. So in the double field theory, so we can consider this ODD transformation, and it would be like this. So at the first, we are puzzled whether there's a mistake or whether we can keep incorporate this thing. I mean, of course, you can trivially incorporate this to multiply a gamma inverse and then you put it in. But still, you see there's the actual term apart from this metric dependence. So that's the M-brane dependence. And for the same anchor, so because this is a homomorphism map, the anchor should be the same no matter for metric or vector fields. So we get the same anchor, and there's how this vector gets mapped along this kind of a global symmetry transformation. So one can then define so this is the vector, and there's the dual one form, and as the dual this 3 vector here. So this is the dual one vector of the 3 form, this one, and in the dual framework, it maps to the 3 vector, and the dual one form is this one. So everything is defined or redefined in this U-dual framework. And I can define this anchor as this. So mathematically, whether this is a proper thing, and then we try to understand from mathematical point of view. When there's a map, we know that know the fact that when there's a map F for the vector space and there's a V and a W. So there exists when there's a map to the R and there's a vector map to the other one. So the matrix defined in this space would so the elements would live in this dual tensor or the vector space. And in our story, what happened is when there's a map gamma corresponding to our anchor, so this gives the Tm to Tm star, and this gamma would be in this space. So the matrix for this, would be in this space. So what happened in the extra term? So for example, the extra term here. So this happened in this recall that in the generalized matrix. Recall that in the generalized matrix. Yeah, so the left upper corner there's a matrix, and when you do the map from this from the generalized matrix and to the dual framework, so the left upper corner is still the matrix, but when you redefine when you want to redefine this this matrix in the I should go back to here. Yeah, for example here. So this is the general matrix and this is the normal matrix. When you do the U-duality transformation and this maps to another thing. So for example, there's the transformation matrix and the transformation matrix here, and you multiply everything together, and then there will be messy matrix. So that is the field that you need to redefine. And what happened is in the U-duality transformation, this upper corner is should be still redefined in such a form. So which means after the field resonation in such a form, the M-brane dependence and also the matrix would be mapped together. But you need to redefine this, redefine the proper matrix again, and there would be the M-brane dependence entered here. And this is what happened here. So the new elements would have the dependence of the M-brane dependence. So in mathematical language, which means under this map for this Tm to the so the Tm is the matrix where lived in. It's enough for Tm. And the Tm will map to the Tm with the sum of the lambda 2 Tm star with the M-brane. And when you want to redefine this proper matrix in the Tm, then there will be this there will be the pullback from this lambda 2 Tm star entered in the Tm. So that will be the extra term here. So which means mathematically it makes sense. And for double field theory, there's no M-brane dependence, so this structure is enough. So this is how we understand from the mathematical point of view. Okay, so now, so after we confirm that this whole map makes sense, let's choose some particular transformation matrix. So remember that we have A, B, C, D here as the most general transformation matrix, and the only constraint is from the special from the S, and the determinant equal to 1 for the transformation matrix. But one can choose a different transformation matrix in particular, and this gives you a different U-dual framework. So for example, here we choose this one. The determinant is indeed 1, and the result would be like this. So this gives in particular global transformation.
And your U is just identity matrix, no? UAV.
Yeah, this is one of the trivial example.
And you have a still non-trivial GT with the identity U.
There's a prefactor comes out here.
V is the flux, right?
Yeah, this represents the flux. Yeah. So let's see the. I didn't write the.
But the U should act on generalized matrix.
Yeah, it's X on the
U
ground.
is trivial. So generalized matrix should not change.
The general metric. So let's see. It's a. I didn't have the little general metric, but
little one, but you act on little generalized matrix.
yeah, the little one it's also has a like the off diagonal is like the v here, and this is a +1 plus v square.
Yeah, but the
Something like
U act on little generalized matrix in a usual way. U small m, U inverse, or something like that.
Yeah.
Then U is trivial. Little generalized matrix never change.
It's I think it's not trivial. So because there's this so this is not just identity, but it's gives the contraction, and so in the end the result is like
That's not identity.
it's not it's different. But there is a
symbol for it.
yeah. So it's not like this. So afterwards, the result is like this. So when you map this, and the other side is the transpose of this. So this was the index structure gets different. So you contract the different one.
Still it's identity, right?
I think it's even the diagonal elements has a non-trivial terms. So this will be defined like this way. So the opposite I know is a vector vi or wi vi wi. So the result is like this. We map together, and there's a contraction is choose different elements from the off diagonal and the diagonal. I mean, we can take later. Okay. So this is produce the result from the Blair's paper, like this one. So this gives the result corresponding to the results then. This is a trivial example, but we can choose a different one, and this corresponds to the B transformation, beta transformation in double field theory, and we choose this one. So the determinant is still 1, and it's allowed. And then then it gives a bit non-trivial general metric in this way. So then the field redefinition would be like this. It's a bit more complicated than what they had in this paper. Okay, so this probably was given in Blair and Professor Park's work related also. So what they did here is that they tried to use the U-duality transformation metric they define this way. So we checked that this is indeed allowed in the general Courant Algebroid anchor mapping. So this transformation metric is allowed, and this will give the if we use this, and this will give the U-duality transformation representing the Busher rule actually. So so for people worked there, they use this to produce the flux like in each step. But if we consider the Courant Algebroid mapping, use this as a transformation metric, and we can directly read off the result for the fluxes. So it's kind of a U-duality version of the Bush rule. So the original Bush rule only for the T-duality. But if we use this, then what produced is not it's beyond the Bush rule with the U-duality. So this so now we see the little generalized matrix. So it's the general version is this. So if we consider the dual part, it's then the v equal to 0 and keep the vector w. So the action is reproduce this. After why I put it here, because when the U-dual redefinition of this vector fields and also the matrix gets all redefined or mapped after the anchor mapping, and then the whole action can be written in terms of the dual fields. So it can reproducing the dual action in the U-dual framework. So the next example is a bit more complicated because we not only consider the M2-brane with the generalized formal sum, this, but also the M5 with the 5 form. So the M5-brane for S05,5, and this is E5. So from the branching root, and we know that the coordinates can be decoupled as 2-3 dependence, this M2 and M5. So now this generalized bundle would be further extended with this. So what we consider is the dual bundle with actual this. Again, we are considering the full global transformation incorporating all the dependence without dropping any of the M-brane. So what happened? What happened would be we take the generalized matrix like this, and we are not taking the section condition to set this, but we take the section condition what need in the algebra closure, and the dualization gives us so to simplify the generalized matrix. So this 3 form are represented in this X and this way here in this matrix. So recall that this matrix and we insert in the action. So the action will be represented, or you call it rewritten by this 3 form purely. You probably also notice that there's no 5 form appear in action. So that's why considering our discussion with the 3 form and the gauge transformation in the Courant Algebroid, that's still enough for this discussion of S05,5. So this is the action, and you insert the generalized matrix, and then you get the proper action from this S05,5 theory. So it again incorporates the diffeomorphism and the gauge transformation. And now we take the general transformation matrix. General transformation matrix in this way. So the index structure to map with the transformation matrix will be like this. And it maps in this way. So we get the dual fields. And the dual bundle is this one for this dual field. So every section is transformed into the dual bundle. So then the result again, so I write it in the simple way. So there's the dirt one, and the structure is like this. So there's this includes the M2 and M5 brane dependence, and it takes, you see, it's much more complicated than when there's only M2 brane, and it's in this way, because there's not just M2 but also M5 brane dependence. It's purely included in this delta term. So again, the reason is because the pullback from the higher dimensional cotangent bundle mapped into the tangent bundle, and then the new defined matrix would have a messy term like this. But here for the simplification, we choose to compute the inverse of the matrix, but the matrix can also be conveniently defined. So this is a three-form field. It's transformed in this way, and then again there's the extra term for the same reason. So there's something. So there's something I would like to mention also. So this is the most general one, and it's complicated like this because we kept all the M-brane dependence. And there's another simple way that if you kill all the off-diagonal elements in the transformation matrix, what this means is the M-brane dependence. It maps, for example, Tm go to Tm star, and lambda 2 Tm star go to this, and there's no mix. So there's no mix terms, mixed transformation. And then it's correspondence to the off-diagonal elements to be 0. But that's in the general way, that's not what we need. Oh, that's not what we want. And if you choose that way, it's still a Courant Algebroid, but it's not. It's a bit trivial. So again, this three vector can be defined in the U-dual transformation, and in the end we arrive in a U-dual background of this SO5,5. So we call this constraint in double field theory. It's often called the weak constraint to get the algebra close. And we take this one and summarize it's like the bundle, this one mapped to this one with this M2, M5 dependence included. Okay, so if we indeed choose the simple transformation, we take this delta 1, 2, 3 to be 0, which means the off-diagonal elements to be 0, and then this will give the map only from for example, the M2-brane dependence to the M2-brane dependence, M5 to M5, and Tm to Tm star. So string to string. And when there's no 0, and then we have the messy general one. So in the simple one, it's like this. And after the field, all the field gets redefined, and then we have the new generalized matrix in the U-dual fields like this. If you insert, so you see there's all tutor on the head. So if you insert this to the action, then you get the U-dual framework. So it kind of indicates that there's a dual theory of this U-dual theory of the exceptional field theory. And the dimension would be 2D if you put them together. Okay, so when we have a higher dimension, what happened? So for example, when we have the D equal to 6 and 7, and then the generalized bundle is like this. So there's another actual term. And whether this can be used from the Courant Algebroid we discussed again, this is the question what we have here. So the generalized matrix is defined in this way. But it's more complicated because the Vierbein is already like this. So I'm not written the generalized matrix out. And so you multiply them together and you see, you can imagine a page messy generalized matrix there. And what happened is, so we know that the dualization of the 3 form and the 6 form is defined this way. The action is like this. So, so this is a dynamic term. So it can be generalized matrix in terms in this way. So you see, there's it's not like S05 form, 5, the 5 form doesn't appear, but here the 6 form indeed appear in the generalized Vierbein and the generalized matrix and also the action. So our discussion with only the 3 form for the Courant Algebroid is not enough. And we need to consider the 6 form, what happened to the 6 form also.
You have 3 blocks of zeros there.
3
blocks of zeros.
Oh, here, this is the Vierbein. Yeah, this is Vierbein. Yeah, so.
And when you rotate by duality.
Yeah, we put the, so you multiply the Vierbein, and then I think there's no zero.
You have,
yeah, but we not rotate the Vierbein, but rotate the generalized matrix.
yeah, but you have to rotate 1/2 index in your Vierbein, M and N.
Yeah.
So you have M and N, and one is duality index, and the other should be local Lagrangian index. Vierbein has 2 index.
So yeah, so we use this to construct the.
So duality should rotate 1 index.
Yeah, right. So we just so we rotate this generalized matrix and we contract this part. Yeah.
Right.
Yeah.
So when you rotate the Vierbein,
yeah,
we know only 1 U.
Yeah. So we contract this and to construct the generalized matrix, and then in principle you can rotate the generalized matrix.
Yeah, and then it's likely you will not preserve these 3 zeros.
Yeah, not
Then
this.
you have to compensate probably to use Lorentz single to rotate and
Okay.
to then equal 0.
Yes, if you want to contract the Vierbein, then you have to consider that. But it's like what we discussed before, or we contract these coordinates, and we have in the general matrix we don't have them. We don't need to consider them. So we first, I mean, this is a bit lazy here. So we use the Vierbein because it's smaller, and in principle we can write multiply them together and contract these coordinates, and then only have a similar generalized matrix, but in a bigger size. And then we rotate the generalized matrix without this.
You obtain the transformation rule from matrix, generalized matrix.
Yeah.
So in principle, you can also use it.
Okay. Yeah. Okay. Yeah. Thank you. So okay. So then as the story we discussed before, and then we can rotate this generalized matrix. And the thing I'm considering here is the new 6 form appear. And what we discussed, for example, the Courant Algebroid exists when there's only gauge gauge field with the 3 form. So that's not enough. And there's the 6 form. So okay. So so what we need to worry a bit about that. But luckily, when we insert all the generalized metric in the kinetic term and in the action, this 6 form is not dynamical in this E6 exceptional field theory, and it doesn't. So in total, it vanished this dependence. So only the 3 form flux, 3 form fields change under this gauge transformation, so that the Courant Algebroid mapping still exists or can be utilized in the E6 exceptional field theory. So this is kind of a theoretical discussion for E6. And what happened for E7? So for E7, there's the field string of the 6 form indeed appear in this kinetic term. It doesn't like the E6, it doesn't appear in the action, so you don't need to worry about the gauge transformation. But for E7, it's indeed appear. And there's another kind of a defect problem, because the E7 is in the 7-dimensional. And to consider this proper duality between this F4 and this F7, one would need to consider 11-dimensional theory. So the defect pump up in two folds. One is we don't have a proper Courant Algebroid mapping for that. The other one is this duality itself with this field string of the 6 form appear. It's not representing. It's not behaving well in the 7-dimensional field theory. So this would be some open question to maybe think about in the future. So this is okay. So we kind of already finished the discussion. So this is how it looks like for the field band, and if you use the generalized metric, so you multiply the field band, contract this index, and you get you can imagine you get a much bigger size of generalized metric, and all the fields here, and this is these are the dual fields of the 6 form. So this is what I mean about the magnetic dual for this. So the 6 form and so the 6 form and the 3 form, and represent the electromagnetic dual in such a way. But again, we don't have enough dimension for that. So the Courant Algebroid, if one wants to study the Courant Algebroid for E7, then we would need to discuss the incorporating of the 6 form to have a large set of Courant Algebroid with the 6 form included. So far we only incorporating the 3 form to have the Courant Algebroid. Okay, so in to clarify, when we consider the ED exceptional field theory, we have this extended bundle, and for E6-7, again there should be. So it's especially for E6, so there should be the dual exceptional field theory structure in the similar way. So from the M-brane dependence entered in the metric redefinition. And for future perspective, or when we summarize, so okay, so So recall that. So we do a redefinition on D-dimensional. Then we have a D-dimensional global symmetry appear, or some people call it hidden symmetry, in the U-dual exceptional field theory. And if we think about this from the double field theory perspective, so for double field theory, so there is a D-dimensional, it's a ODD, because there's a, for example, a D-dimensional supergravity, and there's a dual D-dimensional, people call it beta supergravity. So the whole dimension is 2D. But if we think in the similar way for exceptional field theory, and then the U-dual global symmetry tells you that there's a D-dimensional exceptional field theory, and there's a corresponding D-dimensional U-dual exceptional field theory. So in total, there are 2D. And this 11-dimensional supergravity from M theory. So consider D as consider reduction of D-dimensional at the internal space. So the left is 11 minus D. And if we including the U-dual exceptional field theory, so the total dimension would be 11 plus D actually. So this is what I wrote here. So 11 plus D would be so 15, 16 until 19. When there's a U-dual E4 to till its exceptional field theory presented. So you put like double field theory, you put the supergravity and the T-dual supergravity, and now you have the D-dimensional exceptional theory and the D-dimensional U-dual exceptional field theory, and consider the external 11 minus D dimension. So the total dimension would be like this. And the map for the extended bundle is considered the whole thing to the E star. It's not like we consider this and then we consider this. It's we consider the E to the E star. So this is a global group transformation. So I think theoretically, what it indicates is that so it's there's a double effective theory or M theory, maybe it incorporates, or you can intuitively think there's a dual M theory, U-dual M theory exists. So yeah, so I think that's all. Thank you.
Okay, you would like next speaker for an interesting talk. Are there any questions or comments?
So your last comment.
Yeah.
You are talking about double field theory, reformulation of 11-dimensional supergravity. Am I right?
Double field theory. I think analog to double field theory. Yeah, analog to double field theory. So you have a I propose there's a double the exceptional field theory.
Double the exception. I don't understand double the exception.
Yeah, so double field theory is like you have the T duality as the global symmetry, right? So double exceptional field theory, what I'm thinking is so you have the U duality as the global symmetry, right? That's why we have the
internal.
Yeah.
And then you want to have a double field theory for external. For example, this doesn't work. Right?
Yeah, this perspective is a bit. At some point, I was also confused. So I think the exceptional field theory developed was so from 11-dimensional supergravity, we do the D-dimensional reduction and then find the hidden symmetry, right? And then the D-dimensional hidden symmetry, and then people not restrict by this internal and external, but study the internal field theory itself, and that's the exceptional field theory.
Yeah.
And for exceptional field theory, the hidden symmetry is a global symmetry. So we just focus on the exceptional field theory and use the global symmetry to map another dual exceptional field theory, U-dual exceptional field theory, right? And then you consider this, it's a quite analog to double field theory. It's double exceptional field theory, right? So it's kind of like a double exceptional field theory. But if we want to go back to the former global picture, consider this as an internal. So your internal have a U-dual internal, and the external is still there. So it's a bit like 11 plus D, yeah. So 11 minus D plus D plus 2D. So it's 11 plus D. Yeah, this is what so if we change.
11 plus D is what you mean by that.
Yeah.
Okay.
Yeah. So kind of if we change the view point. Yeah. Indeed, at some point I was confused why they called it internal, and then they consider this kind of study the exceptional field theory by itself. So there was some paper. Yeah, historical reason. I think in some Paris paper maybe, he was talking. He was emphasized that although this was historically internal, but we study itself. Yeah.
More questions or comments? Okay, then I would like to a very elementary question.
Yeah.
The algebroid structure is a direct consequence of duality.
I think it's developed actually in a parallel way, probably. So the algebroid is a bit like what mathematicians do, and the global symmetry and T-duality, and this is like a string theorists do. So it's so for example, when Ralph and me wrote the heterotic double field theory paper, we use the heterotic we use the Lie algebroid with the bundle. Let's see. With the bundle, this one. So it's also not Tm plus Tm star. This is for double field theory. And for heterotic, there is the actual vector bundle for the gauge field for this gauge field A. So, yeah, what was your question? So.
Okay, then let's ask in this way. If you include all higher towers of string modes, can you still expect the existence of algebroid structure?
Yeah, it's a good question. So in heterotic, for example, in heterotic story, so we have this vector bundle, and we checked step by step to compare with the Busher rule. So there we come across a mathematician paper, and they just use this Lie algebroid to study the Busher rule. And physics doesn't realize that. And when we use this Lie algebroid to compare that, so we find that the high order, no, not the high order, the first order alpha prime correction for the heterotic Busher rule was automatically incorporated in this study. That is the first order alpha prime correction.
Thank you.
Thank you.